Hello and welcome. I'm Paige Mitchell and this is my short video on conformations in organic molecules. I hope you're sitting comfortably and ready to learn. Why don't you grab yourself a cup of tea, maybe a biscuit or wherever else you may desire. So, I guess you're ready to learn some chemistry, right? Let's roll on with the video. In this video, I will be covering what conformations are and the names of them, and also why and how they arise. I will then work through some basic examples of the conformers present in molecules of ethane, propane and butane, with explanations on which conformers are preferred and why. Then, to finish off, I will discuss briefly the conformations in cyclohexane. Okay, so what are conformations? Conformations are any of the spatial arrangements which the atoms in a molecule may adopt and freely convert between. Why and how do conformations arise? At room temperature, there is free rotation of atoms or groups of atoms about any single bond in a molecule. Therefore, there are numerous shapes which the molecule can adopt. These are its conformations. Later on, we will find out which conformations are preferred. So, let's put this into practice, starting with a molecule of ethene. A molecule of ethane adopts two different conformations. These are staggered and eclipsed. The two conformations are formed by a 60-degree rotation about the single carbon-carbon bond. A staggered conformation is where all atoms are visible when you view the molecule head-on, like so. Rotate 60 degrees and we have the eclipsed conformation. This is where each of the bonds in the front hides the bonds at the back. We tend to draw conformations as Newman projections, so this is what it would look like for the staggered and the eclipsed conformation of ethane. In this case, the staggered conformation is preferred because it is the lowest energy conformation. The eclipsed conformation, however, is a high energy conformation. This is down to the electron repulsion. There is a greater repulsion in the eclipsed orientation than in the staggered orientation. There is also torsional strain on the bonds in the eclipsed orientation. A further reason is that there is a stabilizing interaction between the CH sigma bond on one CH and the sigma star antibonding orbital on the other carbon-hydrogen bond when in the staggered arrangement. The eclipsed conformation is therefore highly unstable and unfavoured. Only a small amount of rotation will cause the molecule to adopt a staggered conformation once again. The energy changes for the ethane conformations can be demonstrated using a simple graph. The next molecule we'll look at is propane. So, for propane, we can see that the conformations adopted are also staggered and eclipsed. Once again, the staggered conformation is preferred. The same graph plotting energy against dihedral angle can be drawn, but as it is the same as ethane, just with different substituents, I will continue with the video. The final hydrocarbon that we will study is butane. Butane is slightly more complicated than the other hydrocarbons. Butane possesses the following conformations as a result of 60-degree rotations about the central carbon-carbon bond. These are eclipsed, gauche, opposed and anti. Anti and gauche are the preferred conformations, with the lowest energy. Once again, we can visualize this using a simple diagram. For the last part of this video, we shall look at the possible conformations for the structure cyclohexane. Even though when we look at the molecule from above, it looks planar, cyclohexane is not a planar molecule. If it was, it would suffer from angle strain and torsional strain. Angle strain being the amount the bond angles in the ring deviate from the tetrahedral angle of 109.5 degrees, and torsional strain, which is created when the bonds are eclipsed. Therefore, the molecule adopts a chair conformation. where all of the bonds are fully staggered, and so this is the lowest energy conformation possible, where all the bond angles are 109.5 degrees. Here we can see both the chair conformation and the Newman projection. One of the highest energy conformations that can be adopted, but is highly unfavoured, is the half chair. In the half chair conformation, the molecule is inverted. The equatorial and axial hydrogens are all overlapping and ugly looking. Further conformations are the twist boat and the boat. The boat is also a highly unfavoured conformation because the molecule is fully eclipsed and so suffers from torsional strain. Once again, all of these conformations and their relative energies can be shown on a graph similar to the previous ones. It is important to understand that there is free rotation about all single bonds, leading to a variety of conformations. The lowest energy conformations are adopted for longer due to the increased stability of the molecule. I hope you've enjoyed this brief introduction to conformations and that you can now assign names to common conformations in simple alkanes and cyclohexane, as well as explaining which conformations are preferred and why. The links for the sources that I've used are provided above, and I do recommend that you take a look for any further information. Once again, thank you very much for watching.